Arts and Sciences Teleconferencing Service, in cooperation with Oklahoma State University, presents Mathematics, Enrichment for High School.
Good afternoon and welcome to our program. Our topic for today is elementary mathematics for the secondary schools. My name is Wayne Powell and I'm a professor here at Oklahoma State University in the mathematics department. Joining me in this program are two other mathematics professors here at OSU. On my left is Joel Hawk and on my right is John Wolfe. Together we will be addressing three areas in mathematics which we feel might be easily incorporated into your classroom activities. The first topic, which Joel Hawk will present, is on transformational geometry. He will discuss the role of transformational geometry in the secondary school curriculum. Joel will give some examples of introductory material on isometries, as well as provide suggestions for using the ideas of transformational geometry in different courses that are already included in the standard curriculum. And after his presentation, I will discuss some aspects of statistics which I think are accessible to junior and senior high school students. We'll look at some examples from descriptive statistics, where the goal is to represent data in a way that quickly and accurately reflects the values that are involved. Then we'll consider the problem of inferential statistics, and this is a case where a relatively small number of observations are used to draw conclusions about a much larger set of data. And throughout my presentation, I'll try to point out some of the pitfalls that can cause conclusions to be drawn improperly. I'll also make some specific suggestions as to projects that you might be able to use in the classroom. Then the third part of our program will be conducted by John Wolfe and will cover technologies for secondary mathematics instruction. John will discuss using microcomputers to enhance secondary mathematics instruction, and he will also briefly mention a few other technologies that are available for supplementing classroom instruction. These will include videotape series, courses by satellite, and even teleconferencing. Now, John will relay to you what are, in his own words, some of his not-so-successful experiences trying to get these fancy machines to help teach mathematics. Now, before we begin with Joel's presentation, I'd like to review with you the procedures that we'll be following for answering questions and receiving your comments. We, of course, encourage your input at any time, either during this program or at a later date. We have an operator standing by to make a note of any questions that you'd like to have answered today. And we're reserving a portion of the time at the end of the program when we will answer as many questions as possible. If you have a question or comment to give us during the program, just call us at area code 405, and the number is 624-7101. We also welcome any written questions or comments you might have. And these should be addressed to either Joel Hawk, Wayne Powell, or John Wolfe, in care of the Mathematics Department at Oklahoma State University in Stillwater, Oklahoma.
As Wayne mentioned, my topic today is transformational geometry and its place in the high school curriculum. In Oklahoma, we have no courses specifically in high schools about transformational geometry. We offer nothing at Oklahoma State University that is specifically about transformational geometry. Yet several studies, national studies conducted lately, show that there is a place for transformational geometry within existing courses. As one example, the MAA recommendations on the mathematical preparation of teachers shows that transformational geometry relates to several of their objectives. In particular, transformational geometry helps highlight the relationship of geometry to other areas of mathematics and other disciplines as well. The College Board's Educational Equality Project again lists several objectives related to transformational geometry. In particular, the use of concepts of symmetry and congruence, and the use of transformational geometry as a problem-solving tool. I'm going to make suggestions today for ways to incorporate transformational geometry topics into existing high school courses in the mathematics curriculum. My first topic is to discuss the basic transformations or isometries. In the packet that was mailed to the receiving sites, you received some information taken from a module from the series on high school mathematics and its application that discusses translations, rotations, reflections, and glide reflections. The first type of isometry is that of a translation. The graphic you'll see shows that a translation moves everything in a straight line from one position to another without doing any twisting or any turning over, any change of orientation of left and right sides. You can see this picture moving across your screen. The second type of isometry is a rotation. In this type of isometry, one point in the plane remains fixed. Everything else rotates or turns about that one point, maintaining its distance from the center of the rotation. The third type of isometry is a reflection. In this case, an entire line in the plane remains fixed, and everything else is rotated 180 degrees through the third dimension. Equivalently, the effect is that of seeing something in a mirror placed on the line of reflection. Finally, the fourth type of isometry is a glide reflection. This is sort of a hybrid. It's a combination of a translation and a reflection without ever stopping in between. As you can see by the footprint moving across the screen, the footprint has to slide to the right and then reflect across the center line to reach its new position. That composition is called a glide reflection. Isometries are distance-preserving functions. If 2 points are at a distance of 2 units apart before an isometry is applied, after the isometry is applied, they remain in the images 2 units apart. Every isometry is one of these 4. One way to introduce these in the classroom is to look at some wordplay done by Scott Kim called inversions and his calligraphic cartwheels. These take advantage of our ability to recognize letters that have somewhat non-standard forms. The first example is the word Eve, or the name Eve, that is shown in one of your packets in black and white. We also have a graphic of that based on the poster that's done by Scott Kim from which the packet material was taken. There it is, the name Eve done in lilac. He takes advantage there of using a reflection of the letter V across its axis of symmetry. He also uses the symmetry and the flexibility inherent in the letter E. The particular name showed a reflection through a vertical axis that ran through the middle of the V. A second name that illustrates one of these symmetries, or isometries, is the name Bob. In this one, you'll see that the symmetry is a reflection through a vertical axis. Okay, the next name that we could look at, I think, is the name Otto. O-T-T-O, good. This shows rotational symmetry about the point between the two T's. It also shows both a horizontal and vertical reflection. If you consider the axis running vertically between the two T's, there will be a horizontal reflection across that vertical axis, taking one O onto the other and one T onto the second. And there's also a vertical reflection about a line drawn halfway down the letters that reflects the O's onto themselves and the T's onto themselves as well. Another name we have is the name Francine. This one shows a much more artistic idea of the symmetry, much more artistry required to make sense out of this particular name. You can see the Francine there. In this case, the symmetry is that of a rotation about a point in the middle of the word, so that the F that's vertical on the left-hand side becomes the letter E on the right-hand side of the name. This one also shows a little bit more complicated artistic endeavor needed in that the letters R and A together become the letters I and N at the other side of the word. So this is not a case of one letter having symmetry with itself, but rather using a combination of letters to become some other letter. Your students can easily do this kind of work themselves. In fact, it's exciting to let them have a chance at doing this sort of artistic work. A friend of mine took my name, Joel, used the symmetry inherent in the letters J and L, and then did the best she could with the letters O and E to create this version of the word Joel. This has reflectional symmetry across a vertical line. A second one, this is one that I did, was done for the name of Wayne Powell's daughter, Jennifer. I'm kind of proud of this one. This one is also using rotational symmetry, just as did the word Francine. Again, there's some complications here. One advantage of English lettering is that almost anything that happens below the line is ignorable, so that the bottom here of the letter N, which becomes an F after the rotation, can be pretty much ignored in deciphering this. The same way the dot below the line that corresponds to the dot on the I here is ignored when you try to read the word. In making this, or in making any one of these inversions, the basic technique is to decide what the letters will allow you to do. For example, in doing Jennifer, I had to decide what kind of symmetry I wanted to use in changing this name. So I started out with the letter J and went through the different possibilities for the kinds of symmetry I could have. If I looked for symmetry by reflection through a vertical axis, that would mean that I would have to compare that letter with its reflection through a vertical axis, which would turn it around to hook the other way. The R of the name Jennifer would somehow have to come out of this. Okay? In other words, if you look at Jennifer starting with the J and ending with the R, and expected to have symmetry and a reflection across a vertical axis, this J, after it was reflected, would become this, and I would have to use that somehow in making this R. That looked difficult, so I gave that up. Next, I thought about symmetry in a horizontal axis, so I'd have vertical symmetry. This time the letter J would become this, if we reflected through a horizontal axis of symmetry. The J would have to look like itself. That would be possible, I think. One could try making a J that would have a form something like that and have vertical symmetry. But again, I wasn't really happy with the particular outcome I had here. Finally, my last try was to try using the rotational symmetry. This time, I wanted again to compare the letter J with the letter R. To be able to do the comparison, I drew the J and then drew what would happen to the R under a rotation. And tried to see, or tried to think of some way that the J and R could be combined into one particular form. That's where the kind of J used in the word Jennifer came from, namely one that looked like this, taking some of the characteristics from the R and some of the characteristics from the J. That, of course, also forced me to have the R at the other end of the word look like this, and then I had to worry about what to do with all the rest of the letters in between. But that was the evolution of that particular calligraphic cartwheel that gave me the name Jennifer. Once you've introduced these particular topics to your students, you can go on and look at what are called groups of symmetry. Every repeating pattern in the plane, such as a wallpaper pattern, has a group of symmetry that contains two translations. One translation usually horizontally, and another translation at some angle to that, so that we'd have two non-parallel transformations. Of all the possible groups of symmetry in the plane, there are 17 types is all. There are a finite number of types of symmetries in the plane. If you want to analyze what the different forms of symmetry are, it's very useful to devise some sort of flowchart, sort of a field guide to patterns. Included in your packet is a copy of another sheet from the High School Mathematics and Applications module that was produced by Donald Crowe. We're going to use that today to look at two different Escher prints. Escher being the Dutch artist, died in 1972, who was very fond of using repeating patterns in the plane. The first of these shows red wasps and yellow bees. If we run through the flowchart that's shown there, the first question one would ask is, what is the smallest rotation that you see in this particular diagram that brings the pattern back on top of itself? How many degrees are involved in that rotation? The answer turns out to be 120 degrees. We need to get to the other chiron set. which will show that. Okay. We'll show that there's a 120-degree rotation. When you look at the Escher print again, you can see that the center of the rotation would be either at the point common to the abdomens of the insects, or the point where all the left legs of the 3 yellow bees come together, or the point at which the right legs of the 3 yellow bees come together. In any case, there's a 120-degree rotation available, either clockwise or counterclockwise, around any one of those 3 points. So the answer 120 degrees. You can see that we're down in the 4th box then on the handout that was sent out to the individual receiving stations. The next question then is that, is there a reflection in the Escher print? Can you find an axis of reflection that again will bring the picture back on top of itself? The answer to this is yes. What we did was put a different Escher print up first that has opposite answers to these. With the bee and wasp diagram, there is in fact an axis of reflection that runs from the head of any insect through its tail, and you can see that if you do a reflection through that line, you will bring the entire picture back down upon itself. The next question, following through on this particular Escher print, would be to ask if all 3-fold centers are actually on reflection axes. Okay. The answer to this is no. In fact, 2 of the 3 centers, 2 of the centers of reflection that emit 3-fold symmetries, are not on reflection axes. In particular, if you look at the place where all of the legs join, that particular point is not on any reflection axis of the print. The result of this sequence of answers, if you look at your flowchart, is that you end up with a particular group called P31M. Okay. To go through this flowchart with a second picture, let's take a look at the one with birds and fishes. On this one, the birds will be the light-colored creatures, the fishes the darker-colored creatures. Again, if we look at the questions relating to this, the first question is to ask if there are any rotations, and if so, what is the degree of the smallest rotation? In this case, the answer is 180 degrees, centered at either the point common to the 2 left wings and the 2 fish tails, or the 2 bird tails and the 2 left fins of the fish, or the 2 bird heads and the 2 right fins, or the 2 right wings and the 2 right fins. The point is there can be many different possible centers of rotation in these pictures. Okay. So the answer to that one is that there's a 180-degree rotation. The next question is there a reflection illustrated in that Escher print? The answer to that one is no. There are no axes of reflection. That moves us on to asking if there are any glide reflections. And if you look at that particular picture, again, you will find that there are no glide reflections available here. Any way of taking one bird to lay down on top of another one would involve some motion other than that involved in any reflection at all. So the group of symmetry in this particular case is called the group P2, as you can see by looking at your flowchart. The final topic I wanted to talk about today is based on the exercise set from the books of I.M. Yaglom that I sent out again in the packet that was received by the receiving sites. The first of these was a problem that's a familiar problem probably to most of you, but it admits several different solutions, all based on the ideas of transformational geometry, but would be placed in different courses within the curriculum. The problem, and I'll read it to you for those of you that do not have one of the packets, is to use translations to solve the following problem. At what point should a bridge, which we'll label MN, be built across a river separating 2 towns A and B, in order that the path A to M to N across the bridge and on to B, from town A to town B, be as short as possible? The until now unstated assumptions are that the banks of the river are parallel and that the bridge must cross the river perpendicularly. So the diagram here shows the particular kind of problem posed. We want to construct a path from A to B that must move perpendicularly across the river and be as short as possible. One solution to this that could be worked out in a very early class or a geometry class can be solved by the technique of paper folding. In this solution, you simply notice that if you were to fold the paper so that one bank of the river laid down on top of the other, I could connect A and B by a straight line, unfold the paper, and draw in the bridge going from M to N. Of course, what's happened here is that I've applied a translation. I've taken the top half of the paper and moved it down, translated it vertically, so that I've eliminated the river as an object that needs to be crossed. Okay. It's clear here that the shortest distance from A to B would be the straight line. Okay. Moving the paper apart and putting in a bridge there would guarantee that the shortest path from A to B across a bridge would be at points M and N. If I were to look at a bridge that would cross at any other point, I would end up with some path that would not be a straight line from A to B after the translation. Consequently, it would be a farther distance to travel going across the bridge. Okay. A second use of this problem would be in a geometry class in which you're discussing compass and straight edge constructions. This time, instead of folding the paper, we would proceed by constructing a line from A perpendicular to the banks of the river. Okay. We would then lay off the length segment AA prime that would have the same length as the distance across the river. That was how the point A prime would be found. That corresponds, of course, in the paper folding example to having done the folding. The point A was moved to the position A prime by a translation downward in the plane. Then draw the line from A prime to B. The point of intersection with the lower bank of the river, as before, would be the point N. Construct a line perpendicular to the bank of the river to find point M, and finally connect points A and M. All of these constructions can be carried out with compass and straight edge, and manage to incorporate the ideas of transformational geometry in a problem-solving setting within a standard geometry classroom. Okay. Another example of a solution to this problem that would be used in yet another class would be this problem, this solution that incorporates both coordinates and geometry. This time I've set up a coordinate axis using the south bank of the river as the x-axis, using the perpendicular to the point A from the banks of the river as the second axis or y-axis. In this solution, you would set up coordinates for the point A, set up coordinates for the point of intersection of the y-axis with the north bank of the river, find the coordinates of A prime by subtracting the y-coordinate of the point on the bank of the river from the point A. You could calculate the line, the equation of the line from A prime to B, find its x-intercept to find the coordinates of the point N, and then proceed as before to find the point M on the north bank of the river, and so on. So that all of this could be solved by analytic geometry as well. Finally, one last solution, and by far the most complicated, but also one that occurs to people once they've learned about calculus, either in high school or in college, is to use a calculus solution. After all, this is a problem asking us to calculate the shortest something. So it's a problem asking us to calculate a minimum. Again, you would set up a coordinate system. This time, consider a variable point P that could move back and forth along the north bank of the river. You could determine the distance from the path from A to B across the bridge at point P as a formula, and then finish off the computation by trying to minimize that particular formula. Again, this is a solution using coordinates in calculus. It's certainly much more complicated than that would be given directly by transformational geometry. I think if I gave this problem in a calculus class, I would also be very careful to point out that there were other solutions possible after the class had done it by calculus, so that they could see that not all max-min problems needed to be solved using the techniques of calculus. One last problem, and then I'll finish with my part, is the second problem on the sheet that was sent out to the receiving sites. This problem states the following. Use a rotation to solve the following. Given two circles, S and T of possibly different radii, that intersect in a point A, pass a line through the point A so that the line M cuts off equal chords from both S and T. It's a little more complicated to state and is stated in terms strictly of geometrical concepts, but the reason I wanted to present it is that the solution I find particularly elegant. The first step in the solution is to rotate the circle S 180 degrees about the point A. So we'll do a half turn about the point A to obtain a new circle we'll call S prime. Once we've done that, we can then draw a line that passes through the point A and the point of intersection of the circle S prime with the circle T. And we get this picture. This is the line M we're looking for. Why? Well, because having done the 180 degree rotation, the circle S passing to the circle S prime would pass this point on S and the line M to this point on the line S prime. The line M in the circle S prime. Consequently, the distance from A to this point on the circle S is the same as the distance from A to this point on the circle S prime. The reason that solves the problem, of course, is that this line from A to this intersection point is not only a chord of S prime, it's also a chord of T, which consequently is a chord of the same length as the chord we drew through the circle S. So that line M is the line we're looking for. How can you use this? Again, this same problem could be used in several different situations. It could be constructed by actual compass and straight edge construction in geometry class. It would also be possible to carry out this idea using coordinate systems. I'll now turn the podium over to our next speaker, Wayne Powell, who will speak to you on the topic of statistics in the high school curriculum.
Thank you, Joel. As I mentioned earlier, I'm going to be discussing some topics in elementary statistics which I think can be easily integrated into your classroom activities. And my goal is to show you some of the techniques which are used in everyday applications, and also to point out some of the cautions that need to be taken to avoid the misuse of statistics. The intent in addressing some of the difficulties is not going to be to discourage you from the use of statistics, but rather to give you a better appreciation for its implications. Basically, the field of statistics can be broken down into two very general categories, and these are known as descriptive statistics and inferential statistics. The first of these, the descriptive statistics, includes the presenting and summarizing of data. It does not go further than this by trying to draw conclusions about a larger set of data, but rather it limits itself to simply presenting things in as clear a fashion as possible, in a way to reflect as much information as is available. Now, the process of using the information to make conclusions or inferences makes up this second branch, which we call inferential statistics. And frequently, the goal in inferential statistics is to use a small set of data to determine the properties of a much larger set. Okay, let's begin by looking at some of the examples of descriptive statistics. We'll start by taking a chart that shows some test scores of a group of students on an exam. So as you can see, these student scores are listed in groupings of 10. So we have from 30 to 39, 40 to 49, up through 90 to 99. And they're so listed for who knows what reason, but probably because these are the only scores that were available on that particular exam. And one thing to notice from this chart is that it does not show the precise scores of the individual students, but rather it presents them to us as grouped data. And what we want to be able to do with this information is to graphically represent it in a way that shows the relative number of scores in each classification. Now, one of the best ways to do this is with a graph known as a histogram. Now the second chart I'm going to put up shows an example of such a graph. The overall intent of this kind of a graph is to reflect the relative number of students in each score classification by drawing boxes or rectangles. And there are several characterizations of this histogram which stand out that I want to point out to you to begin with. First of all, notice that the grouped observations are placed on the horizontal axis and they're evenly spaced. In this case, the grouped observations refer to the score ranges of the students on the exam. Then the second thing to notice is that the frequency of occurrence is listed on the vertical axis. And in this case, this is the number of students in each score range. Then the third point, which is probably the most important in constructing a histogram, is that the rectangles are drawn in such a way so that the bases reflect the class intervals and the areas reflect the frequency. Now this last property is one of the main keys that we need to follow to accurately reflect the properties of the distribution of test scores. That is, the areas of the rectangles are supposed to be the main tool that correspond to the relative frequencies of the groups. Okay, let's go back to the chart of data just for a minute so we can look at it before we look at some other histograms. Notice again that each of the classifications for the scores was the same size, that it was a 10-point interval. And such a table of values is usually easy to represent with a histogram, but scores unfortunately are often not given to us in such a nice fashion. For example, suppose we consider this next chart here. In this case, we don't have the things grouped as A, B, C, D, and this time we don't have the test scores grouped by intervals of 10, but rather they're grouped as letter grades of A, B, C, D, and F. Now this chart represents the same test scores, but this time all the Fs are grouped together into a single classification. So you can notice we still have 10 Ds, 15 Cs, 10 Bs, and 8 As. But then the three groupings of Fs are all put in the range of 30 to 59 rather than spreading them out into intervals of 10. Now there's no problem with this kind of a table if all we want to do is represent the relative number of letter grades that were received on this particular test. But if, however, we want to use this information to represent the distribution of numerical scores, then we have to be more careful since the grouping of the scores given here are of unequal length. Now we'll look at a couple of examples of histograms that were created to attempt to describe this data. Okay, our first one here is going to show a common mistake that's used in the creation of histograms in representing data such as this. Now in this histogram that we're going to put up, notice that the rectangles for the A, B, C, and D classifications are still exactly the same as in the first histogram we viewed. However, the preparer had some difficulty in deciding what to do with the F grouping. Since the total number of Fs is 14, he chose to make the rectangle have height 14. And also, since the width of the F range was 30 points now instead of 10, he made the rectangle 3 times as wide as the others. Now the overall effect is that the histogram gives a visual impression that the Fs dominated the test grades, which in fact really isn't true because there were 14 and they're spread out over an interval of 30 points rather than all in one 10-point interval. So the problem is with this histogram is that it broke the rule that I mentioned earlier. There was rule number 3 about keeping the areas of the rectangles as the main tool for comparison. Okay, let's take another histogram which does a better job of visually representing the distribution of scores. Now in this case, what the preparer did with this histogram is he again chose a width for the Fs which is 3 times that of the other classifications. And that's appropriate because the F range that we were given here actually was 3 times as wide. But instead of making the height 14 like in the previous histogram, it was made to be 14/3, or in other words almost 5. And what that represents is the frequency of the Fs divided by 3 because the range for the Fs is 3 times as large as for the other regions. Now this is the best way to draw a histogram to describe a distribution such as this where the groupings have unequal lengths. That is, you want to key in on the width of the intervals and then make the areas of the rectangles correspond to the actual sizes of the groupings or of the frequencies. So one of the keys to representing data with a histogram is to make sure that the visual effect corresponds to the real relationships between the frequencies and the groups. Now let's consider a possible project for classroom use. What I'm going to suggest you do here is that you give your students a table of data which has unequal width groupings, such as the last one that we just gave for the test scores. Then when you do this, have them create some histograms which are intended to depict the relative frequencies of the distribution. Now, I'd recommend doing this before the students have been shown problems that arise in making histograms for these kinds of distributions with unequal groupings. And that way, they'll be more likely to see for themselves what the difficulties are in representing data where the groupings have unequal sizes. Okay, let's go on to another topic of representing data, so another phase of descriptive statistics, which is similar to that of drawing a histogram. And this is what we're going to look at here is a graph called a frequency polygon. And this kind of a graph can be very useful in depicting relationships between data, or it can be very misleading. So let's take this first table we've got up here. Now, this table gives the percent of families in the United States who own their own homes during various years. I believe we start with 1965 and go in 5-year intervals up to 1985. Now, as we look at this data, what we want to do is create a graph which will represent the changes from one year to the next in the percent of home ownership. Now, there are several ways of doing this. And as we'll see, we're going to draw several graphs which we call frequency polygons, and depending on how they're constructed, we can either show that there's been virtually no change in home ownership from between 65 and 85, or we can show that the shift has been radical. So it depends on the method that's used for construction. Okay, so what I did is I gave this information to some students to draw some graphs, and I got some varied results. The first graph we're going to put up shows what one student's perspective was on the values of the distribution. Now, as we look at this graph, I want to first point out a few things about the construction of a frequency polygon in general, and then we'll come back and look at the specifics of this particular polygon. The steps for constructing a frequency polygon are the following. First thing you do is you put the classifications on the horizontal axis. Now, that's similar to what we did with a histogram. Here our classifications refer to the years 1965 up through 1985. Then our next step is to put the frequencies on the vertical axis. Now, in this case, the person listed all the frequencies, meaning the percent scores in this case, from 0 up to 100, because those describe the possible percents that we could have for home ownership. Then after that's done, after you get the axes correctly labeled, you put paired values plotting on the graph. And that means for each year, you put the corresponding percent and put a point up there. Then the final step for completing the frequency polygon is to connect the adjacent dots. And the result we have is a graph which shows the relative values of the distribution. Now, all frequency polygons are constructed in a similar manner as this, but the results can be quite different even for the same set of data. So let's look carefully at this particular frequency polygon again, as it relates to the information that we were given. Now, the vertical axis here gives all possible percents from 0 to 100. And since the only percents found in our table were between 63% and 64.8%, the result is that all the information is compacted into a very small interval. And the viewer will leave this graph with the impression that there has been almost no change in home ownership between 1965 and 1985, because our graph appears to be essentially a horizontal line. Now let's move on to one more frequency polygon where we'll see a quite different result. In this case, the preparer chose to make the polygon in a slightly different manner. Notice that the main difference here is in the scale that was used on the vertical axis, representing a percent that represents the percent of home ownership. Now, this time the range, rather than being from 0 to 100, is restricted to between a general range which our scores fell. So they put 60 to 65, and our scores actually were between 63 and 65. So consequently, this graph gives us the impression that there's been quite a bit of shift in home ownership from 1965 to 1985. So one of the points which I'm trying to make is that it's very easy to convince the casual observer of whatever point you were trying to make with a frequency polygon. Now, a case in point is comes from a recent article in the New York Times. The New York Times had essentially the same data available to them as we had for this percent of home ownership. There's only one difference in what they had, and that is that they had values for home ownership for not just at 5-year intervals, but rather at 1-year intervals. So they had a little bit more information in preparing their frequency polygon. Let's see if we can get a shot of this polygon. We'll show what the New York Times came up with. Now, as you can see here in their graph, down here at the bottom, they show again the years, 1965 and 5-year intervals, and then this last one is 1986. For some reason, they chose to skip up there. Then on the vertical axis in the graph, they start with 63, go up to 63.4, and skip at intervals of 0.4 going on up the vertical axis. And they have a little more jumping around in their graph because they have yearly figures rather than just five-year figures. Now, as you can see from looking at this graph, it appears that there's been quite a great deal of fluctuation in home ownership in the time from 1965, or in their case, up to 1986. Now, in my opinion, this is probably the poorest of the three graphs we've shown because it makes no attempt to point out that the expanded vertical scale here really distorts the overall graph. Okay, this brings up another project which you can use with your classes to help point out the care that must be taken in presenting statistics. This project I would recommend that you have your students do is I'd recommend you have them construct some frequency polygons to demonstrate different conclusions from the same data. So what I'd suggest doing is that you give a table of data to several students and then give each individual in the group a different impression which you want them to convey to the outsider. Then they should be able to create frequency polygons, each of which will cause the viewer to come away with a different kind of conclusion. Now the hope is that this will not discourage the students from drawing frequency polygons, but rather will give them a better appreciation for what's involved in accurately representing the data. Now, the act of drawing conclusions from data lends itself to the second main branch of statistics that I want to address, and that's the inferential statistics. Now, in this case, we want to take, again, as I said before, a relatively small set of data and use it to draw some conclusions about some much larger phenomenon. Now, this branch of statistics is vast, and we can only touch on some of the cautions that need to be taken. But what we're going to look at briefly is a series of examples where samples are used to predict something about a much larger population. And in each case where we look at these samples, I'll try to give you an example of how incorrect inferences can be made if you're not careful. Now, the first example we're going to look at is one that we'll be faced with more and more in the coming years, and that's the political poll that we're inundated with constantly during election years. And we regularly see these reports which tell us what our political preferences are on candidates or various issues. And it might be interesting for you and your students to try to follow the different polls, because sometimes you'll find out that different pollsters come up with different results, and frequently this is caused just by asking questions in a different way. You also might want to try to wait till election day and check the validity of some of the presidential polls to see if the percents actually come out in a similar fashion to what they were predicted to be. Now, one thing I'd like to point out is that in recent years, the results of these political polls have become much more consistent and reliable. But there still have been some classic blunders that have happened over the years. Perhaps the most famous one is one I'd like to mention here, and this happened back in the 1930s by a magazine called the Literary Digest. This is a conclusion that they drew. In 1936, the Literary Digest ran the results of a political poll that showed that Alf Landon was the probable winner over Franklin Roosevelt in the presidential election. Now, of course, we all know that Roosevelt won the 1936 election by one of the biggest landslides in history. The problem with the poll then? Well, the Literary Digest interviewed people only from a list that came from its subscribers and from people who owned telephones. And as the country was emerging from a depression in 1936, only the more affluent people would have telephones or subscribe to a magazine. So this made essentially the results of the poll to be inconclusive, and in fact they distorted the actual result. Now, what happened to the Literary Digest? Well, the Literary Digest after this essentially lost much of its respect in the magazine world and survived only a few more years before discontinuing publication. So whether or not that was caused by their poll about Alf Landon is uncertain, but there is some implication it probably was. Now, another place where samples are used frequently in our everyday world is in quality control. If a company wants to check for possible defects in their product, they're unlikely to examine every item because of expense and time. Rather, what they choose to do is to check a small sample of the product and use this to draw conclusions about the product in general. And this is fine. In fact, it's very efficient if care is taken in the method that they use for determining the sample, that is, in selection. However, it's very easy to choose a method of sampling which can on first appearance seem to be legitimate, but on close examination can be found to have a serious flaw to it. Now, here's one case that I'll give you which caused a serious problem for a company that bottled, I think a soft drink is what it was. What the bottling company did is they automatically checked every 30th bottle that came off the line to make sure it was correctly sealed. Now, the problem arose in this method of sampling in that the machine responsible for sealing the bottles had a periodic glitch in it. And this problem with the machine caused an improperly sealed bottle every 60th time that one came through the machine. Now, the interval for checking was every 30th time, and the interval for the problems was every 60th time. So the result is that since the interval for checking was or the interval for mistakes was a constant multiple of the interval for checking, then either none of the mistaken bottles were found or all of them were. In this particular case I'm referring to, it turns out that none of the bottles were found and they all were verified as being in good shape. Now, it doesn't take someone who doesn't know much about statistics to make errors in choosing samples. A case not too dissimilar to the sampling by the bottling company arose when a university wanted to check on the success of its graduates. This is what the university did. They sent out questionnaires to their graduates asking them to report on their careers and salary ranges. Many of you who have been to college have probably received questionnaires very similar to this. Now, when people responded, they naturally, the ones who did respond were the ones who were more successful in their careers and had higher salaries. The people that were having problems financially were not apt to respond and tell what their salary range was. So the consequence is that the salary range that the university thought their graduates were in is actually reported as much higher than it really was. Of course, the university wasn't too disappointed at this because they like to be able to report a high salary range from their poll. Now here's another class project which might help your students to appreciate the care that must be taken in drawing conclusions from sample data. What I'd like you to try this time is to find an issue which is of interest to your entire class, and then have each student independently conduct a poll on the issue and carefully record all their techniques. And after you're through, compare their results. And my guess is that many of the polls are going to have very similar results. But for those that don't, have the class examine the details of the sampling procedure to see if a flaw might exist. In any case, I think the students will enjoy the process of designing a method of sampling, conducting the poll, and analyzing the results. Furthermore, they should gain some appreciation for the polling process. One thing I do want to caution you in creating a poll is that it's usually better, especially at the early stages, if you have your students create a poll that the possibilities for answers be either yes or no. For example, we had one class that created a poll where they went in and asked other students what their favorite food was or what their favorite television program was. And the results is, when it came to the favorite television program, they had about 50 different classifications with two or three groups in each classification. So essentially they didn't find out any real information. Now, what they probably should have done in designing the poll is pick out 2 or 3 programs and ask students to vote on between those which was the most popular. And then they could draw a conclusion based on that information. Now here's another place where your students might be encouraged to conduct polls. In recent years, you may have noticed that there's a rash of what I call non-scientific polls, which are conducted by the media usually. They appear in magazines or in newspapers or sometimes on television stations. I regularly find in particular reader polls in magazines or viewer polls on the evening news, and they're usually followed with a disclaimer that says there's really no scientific basis to these polls. But unfortunately, even though they have the disclaimer, they spend most of their time showing the viewers what their results are, and consequently the viewers come away with the impression that the poll is scientific. The way these polls are usually done is they'll put up an issue, like whether or not the people were supported something that happened in the government today, and ask the people that support it to call in on one phone number and the people that don't to call in on another phone number. But there are generally a group of people who tend to be more excitable by these issues, and of course they are the ones that respond. So essentially the poll has no significance except just as a curiosity item. And what I'd suggest you might try to do is take one of these polls, have your students watch for them, and then have them take a poll on the same issue, where they go out and find as random a sample as possible and conduct the poll with the same issue and compare it to the results that the station or the newspaper was advertising, and see if there are any similarities at all in what they've arrived at. Okay, now there are many other topics in statistics which can be addressed in the secondary schools and which can help make your statistical world more meaningful. If you do have questions or comments on these topics or some of the others in this program, I want to encourage you to call us today or write to us. And again, the phone number at which we might be reached during the program is area code 405, and it's 624-7101. If you would prefer to write to us, we will again put up the address where we can be reached while we're getting ready for John Wolf's presentation on technologies for mathematics instruction.
Okay, excuse me just a minute here till I get things organized. Also take my watch off here. I'd feel a little better if I were doing talking about the quadratic formula or something like that. Okay. My name's John Wolf. I teach mathematics here at Oklahoma State University. I'm also very much interested in the world of sort of high technology, and in particular, its applications to teaching math. I'm called this presentation Technologies in Secondary Mathematics Education. And certainly when we think of technologies, primarily we think of computers. Apples, IBM PCs, Ataris, Commodores, and that's what I'll talk about mainly. I'll talk about the computer. I will, if time permits, at the end I'll talk about a few other interesting technologies, videotapes, teleconferencing, and things of that sort. I do want to make one point very strongly at the beginning. I'm talking about using computers to teach mathematics. When we think of computers, normally we think of, particularly in the school system, we think of word processing, computer literacy, programming, basic programming, this sort of thing. Those are great, and I think it's very good that high school students are learning this, and we can see it in the universities. The students are better prepared in terms of their programming skills. They're good. Those are good skills to have. They're marketable, whether it's a bull market or a bear market. But that's not what I'm talking about. I'm talking about teaching mathematics, specifically at the secondary level, and using computers as a tool. So I want to emphasize again, mathematics. So I'm talking about teaching algebra, teaching the quadratic formula, how to graph polynomials, how to draw trig functions, the sorts of things that we do every day as math teachers. How will the computer help us do that sort of thing? Now, frankly, I'm not an expert on this area. I'm rather new to using computers to teach mathematics. The fact is, I graduated more than 5 years ago, and since computers have only been around about 10 years, and they're used more widely in education now, but when I went to school, we didn't have microcomputers, so it's sort of a new thing. About 4 years ago, when I came to my office, there was this big pile of boxes outside my office door, and there it was. I had a computer, so I sort of entered the microcomputer age. And the chairman told me that we had gotten several $100,000 in computing equipment and given at a cut rate price, and that the reason we were given this computer equipment was so we could use it to teach mathematics and sort of show the world what good computers are for teaching mathematics. So he told me, I told him, none of us know anything about computers and using it to teach. And he said that, well, we have to learn, okay? So I was sort of forced to learn how to deal with using computers in instruction. So I'm really going to relay to you some of my experiences in attempting to use computers to help us teach mathematics. Some of them have been successful, some of them not quite so successful, usually interesting, sometimes humorous, but not fascinating. Okay, and now before I actually start on the sort of formal presentation, I'd like to mention that I will, at the end, toward the end of the program, and in fact, after, we're going to see about 3 video sequences here, and after the second one, if there are any questions, I'd like to attempt to answer them live. I'd be real happy to get calls, particularly from high school teachers, to find out what the situation is at your school, what your computer situation is, what are your experiences in attempting to use a computer to teach mathematics. So there are people online who will answer your calls. The lines are open now. You can call in and they'll record your questions and we'll answer them toward the end of the program. And then in a few minutes, if there's someone on the line, I'll try to attempt a live phone call. And by the way, feel free to call in and comment with questions and comments on the earlier programs. For the last 15 minutes or so of the program, we'll open it up for questions. So I've been I've been working with computers. I've had a computer. That box appeared outside of my office about 4 years ago. When I first got my computer, I thought, well, who do I call? Who do I talk to find out how we use these to teach mathematics? I want to emphasize again, I'm talking about secondary mathematics. The fact of the matter is that computers have had really very little impact on secondary mathematics. I'd like you to show you two statistics here. These statistics are from a national survey of instructional use of computers. They're from 1985. It's the most current statistics available that I've been able to find. They were in last month's issue of the NCTM News Bulletin. I was struck by these statistics. The first one says 25% of math computer use is in grades K through 2. So 25% of the usage of computers to teach math is in grades K through 2. Math Blaster works. So Math Blaster is a great program for teaching kids how to multiply, how to add, that sort of thing. How about the second statistic? Algebra and geometry occupy 2% of computer time in grades 9 and 10. 2% in grades 9 and 10, 25% in grades K through 2. I'll refer to these statistics several times during my presentation. That first one I think of as the Math Blaster statistic, and the last one is the algebra and geometry statistic. Last summer, I worked with about 60 high school students who were bused in here to Oklahoma State University as part of sort of a summer youth job training program. There were 60 students. They divided up into 3 sections of 20 students each, and I worked with them over a period of 2 months. For the first month, we worked on problem solving, and the second month, we worked on computers. We worked in a math lab with various computer activities. I don't believe these students would mind if I said that they weren't the most enthusiastic students about mathematics. In fact, many of them had, at least some of them, had a history of not being particularly successful in their mathematics work. I'd like to show you now a short video sequence of some of the activities of these students. This is a picture of the Math Learning Resources Center where the students met. I sort of call this video sequence "Computers Are Captivating." Computers do really grab a hold of students' imagination. They're fascinated with computers. You notice there that he was playing with the computer instead of listening to his Walkman. This is Mark Wilkinson. He's from Chandler High School. Cassandra Freeman from Stillwater. I think she's in 11th grade. Here's Cindy Cavanaugh. Cindy doesn't particularly like mathematics, and I had a great deal of trouble keeping her attention during the problem-solving portion of this summer program. But you can see she really likes the computer. She's wrapped up in it. I've only ever seen one student asleep in front of a computer. One time there was a student who fell asleep in front of my computer. I'm not going to tell you how many students I've seen asleep in my class. I think computer phobia, we read a lot about that. We hear about that, about people being afraid of computers, and maybe we confuse it with math phobia or something like that. Students generally have a very good, very positive attitude toward computers. They're ready to get on there and see what they can do with them. I think maybe computer phobia is more common among the people over 30, certainly not among students. And if you still don't really believe me that computers are very captivating, we should go to a video parlor, and you'll see people spending hundreds of dollars on computers. How do we use them to teach math? Well, I think we should think of a computer as being sort of like a VCR, like a slide projector, like a transparency projector, something like that. It's a tool that we use to give an alternate approach, an alternate way of making a mathematical point. Okay. So, and it's certainly a good idea in whatever we're teaching to have several ways to present it. Maybe we have a transparency. Maybe we have a picture out of the book. Maybe we have a diagram. At times, the computer offers an excellent way to make some mathematical point. And we should think of it that way. So it doesn't teach the entire mathematics, but it's one of several aids that we can use in teaching mathematics. It works great with some topics. Math Blaster works great for teaching multiplication. Now, I'm emphasizing secondary level. Computers are great for teaching graphics, drawing graphs, polynomials, trig functions. They don't work so good for doing the rules of exponents in algebra, this sort of thing. They're great for transformational geometry ideas. They're great for compiling statistics, this sort of thing. They're great ways of supplementing our instruction in some areas, others they don't. We use them whenever they apply, just like we use slide projector, just like we use pictures from a book. There's a big headache with computers, though. It's a little more complicated to use than say, a chart that we hang up in the classroom or a blackboard. For one thing, they're a little more expensive. We need to have the equipment. We have to have equipment. There's compatibility problems, that sort of thing. There's also scheduling problems. Quite often computers in the school systems, the computers will be located in a micro lab, that sort of thing. And when do the math classes have access to that lab? Quite often the labs are reserved for computer science courses, for programming courses, computer literacy courses, and we as math people don't have access to the courses, or have access to the lab facilities. I think one of the problems there, I think it's important for schools to have sort of general use microcomputer labs that can be scheduled at times to be used for mathematics demonstrations. You know, we need them unevenly. When we're in an algebra course, when we're doing exponents, we probably can't use a computer too much there. When we're graphing functions, when we're trying to draw the graph of a parabola, something like that, graphs of trig functions, sine functions, computers are quite handy to do computer demonstrations, to have the students work out examples. So then that's when we need the computer lab. So I think it's important for schools and math teachers to insist that they have access to computer facilities. I think it's a great idea to have a computer in the math classroom, and there are all sorts of things that you can do with a computer. You can do demonstrations for the students, or you can assign activities, have individual students working with the computer. Another good idea is for math departments to have a microcomputer on wheels, so that when you need it, you can wheel it into your classroom and use it, and then they can use it. Other people can use it on other days. Even make arrangements with other departments, with physics or with language arts, other departments to share computer facilities. Computers should be available for content areas. And largely, I believe now, in the secondary schools particularly, they're monopolized for programming and computer literacy. So I think we as math teachers should insist that we have access to computer facilities for training in the core curriculum. Well, I've argued that you should you get a hold of a computer and get one in your classroom, or insist that you have access to the microcomputer lab. Well, after you stick your neck out, insist on getting a computer in your classroom, what do? That'll take care of itself. Remember the story I told about the boxes outside of my office. I've slowly learned ways to use the computer in my courses, and I think you will too. Be patient though, and you'll have a few failures along the way, but just work on finding a few demonstrations, a few activities the first semester, and over a period of years you'll build up more and more places to use the computer in your instruction. Well, enough of my harangues about computers in education. Let's look here at another video sequence. This sequence I call Computers Release Creativity. These are some more shots from last summer. You'll see students working with a program called DR Graph. It represents data in various formats. Here you can see a nice pie graph. It also draws bar graphs, sticks graphs, that sort of thing. That's Mark Wilkinson with his Toyota repair data. This is Loretta Williams. You can't read it too well. It says, who really wins, Coke, Pepsi, or Dr. Pepper? The final test, it says. Dr. Pepper is the most popular among our class. So that data is from our class. When you use computers, it rarely works out quite the way you planned it to. Now, fortunately, it often works out. It works out better as often as it works out worse, and you frequently find you have very interesting experiences. Often, some of those sort of memorable experiences we have as teachers that we remember for the rest of our life. Now, here's one example, I think, of creativity sort of led astray. I don't even know what this graph means, but she was being very creative. And here's our final example of something that didn't work out quite like it was supposed to. So it wasn't really mathematics there, but that was James. He did learn how to use the editor very well. Let me check on my time here to see how. I'm going to make a quick comment, and then we're going to see another video sequence. One of the things that makes it a little bit difficult to use computers in teaching, I think, is the fact that none of us were taught that way. You know, as teachers, what we really do is, I know in my case, there are several teachers I had a great deal of respect for when I was in high school and in college, and I frequently adopt their teaching styles and their teaching methods. And I never had courses specifically on how to teach math, but I picked it up. I had experience. In the case of computers, no one who's over 25 would probably use computers when they were in high school. They just weren't around then. So it's really a wide open world. How do we use computers? What are the ways? What are the ways to do it? And it's one of these things where I think mainly you just have to give it a try. Try things. You'll mess up now and then, but you'll slowly develop sort of the expertise, how to handle it, how to funnel the creativity that the computers unleash, how to funnel that into mathematics. We've seen two video sequences here, and we haven't seen too much mathematics yet. I'd like to show you another segment which has some computer demonstrations. We'll get a little bit closer to core mathematics. So let's have a look at some of the mathematical ideas that computers can express. By the way, after this segment, if there are any of you would like to call in with a comment, a phone call of any sort, I'd really be quite happy to try to respond as best I can. And I'd be real glad to hear comments about your experiences in trying to use computers to teach mathematics. I'm sure the math teachers among you recognize this is a family of cubics. Computers are very good at drawing graphs, and they're very good at getting across getting across the idea, the connection between an equation and a graph. Here's another family of curves, and here you can, the degree increases. There are a lot of good electronic chalkboard type programs available, really for many kind of computer. Certainly it's better to have one of the newer computers that has higher resolution graphics, and it's faster to represent this sort of thing. Computers are very good for developing geometric intuition, problems, various kinds of geometric concepts. There are graphing packages available to draw pie charts, bar charts. We saw that with DR Graph in that last video sequence. This demonstration here is from UMath. So it's calculating, you probably can't see it too well on your screen, but that's calculating factorials up as far as 100 factorial. And in a second, UMath is a symbolic calculator program. Here it's calculating x plus 1 to various powers, x plus 1 to the 5th, x plus 1 quantity to the 6th, up through x plus 1 quantity to the 10th. So UMath is a symbolic calculator. These demonstrations here, by the way, I chose because they're big and it scrolls across the screen. UMath is a very powerful calculator, and I don't think its full potential for teaching mathematics hasn't been realized. The student uses it as a calculator. You plug in a problem, type in a problem, hit return, and it calculates the answer for you. And it does all sorts of sophisticated things. It does algebra, does calculus, differentiation, integration, solves equations, solves quadratics, all sorts of very nice mathematical applications. This last program on the demonstration shows, well, it's sort of another graphing thing. This shows you it shows us the phenomenon here is beats or resonance. It shows you how good computers can represent sine waves, that sort of thing. This is part of a package used here to teach differential equations, but a similar sort of thing could certainly be used in connection with trigonometry. Okay. I'd like to mention one other, I think, fairly common misconception about computers in mathematics. One thing is that there are lots of computer demonstration. Well, you know, given the situation where we grew up before computers are around, many of us don't have much experience with computing. And the fact is, you don't need a lot. You don't need to know BASIC, for instance, and certainly the students don't need to know BASIC. In fact, the students don't even have to be computer literate to use computers. Remember the Math Blaster statistics. They use computers to teach mathematics in kindergartens. In fact, they use computers in K through 2 more than in 10th grade, and those students are not computer literate. So it's a misconception to think that the students need to know a programming language such as BASIC to use computers. All those demonstrations were prepared at the Math Learning Resources Center here at Oklahoma State University, and the students don't need to know BASIC to use them. There's a menu, they make selections, they see the demonstrations, they change the parameters and see the results. So I think it's important to realize that in order to really effectively use computers in our instruction, we ourselves don't have to know BASIC, that sort of thing. We do have to be computer literate. You've got to get a hold of a computer and play around with it a little bit so you feel comfortable with it. But to use it, you've got to experiment with programs, and then try it. I think the main thing isn't programming specifically. You don't need to know how to program, but it sort of takes a sense of adventure, that sort of thing. Get out there in the class and try it. You'll screw up a little bit, I'm sure, just like I've done many times. But I mean, it's really a quite enjoyable experience. I think that if I were to summarize in one sentence, really what I'm trying to say about mathematics and computers is that it's really a wide open area. There's lots of room for various people like us, non-experts, people who just happen to get access to a computer to try to use it to teach mathematics. Computers and education is a wide open area. I think you should join in all the fun. Okay, that's the end of my formal part of the presentation. I'll go over here and join Wayne and Joel, and we'll try to respond to a few questions.
John, in fact, we had a question from a young lady in McAllister, Oklahoma, aimed at my transformational geometry presentation.
Okay, you take over
thank you.
Take over the podium.
Yeah, Shannon Giacomo in McAllister would like me to discuss the answer to question number 3 on the translational geometry handout that was received at the receiving sites. That particular question asked us to use a reflection to solve the following problem. Given a line and 2 points on one side of the line, find a point on the line so that the angles formed from the points A and B to the point on the line are equal, are congruent. This can be viewed as a billiard ball problem. If you're trying to shoot a billiard ball from point A to point B while caroming once off a cushion that's a straight line, and you have no English on the ball, what you would ask for is for the ball to run from point A to point B, bouncing once off this line. Here is one way of solving this particular problem. If you take a reflection of the point B through the line to the point B prime, draw the straight line from point A to point B prime, the two angles formed, AX out this way to M, angle AXM, and angle B prime XN are guaranteed to be congruent, of course, because those are vertical angles formed by the intersection of two lines. The two angles BXN and B prime XN are also guaranteed to be congruent because we've applied a reflection. So we have a second pair of congruences, second pair of congruent angles, and the consequence is that all three of the angles that I have marked here are congruent to each other, so that the line from A to X and then the line from X to B form congruent angles with the given line MN. While I'm here, I'd also like to take the opportunity to talk about problem 4, because the answer is very much similar to the problem that we just solved. Question 4 asks the same thing. We have a line M and 2 points A, B on one side of that line. This time we're asked to find a point X on the line so that the sum of the distances from A to X and from X to B is as small as possible. In other words, we're trying to race from point A to point B while touching the line and trying to do this in as short a distance as we can. Okay. To describe this, if we look at this picture with a point X prime marked on line M, we're trying to find the position of X prime that will guarantee that the sum of this distance plus this distance is as small as can be. The solution to this, by using transformational geometry again, is to translate the point B through the line M to find the point B prime. The line drawn from A to B prime will intersect the line M and the point we're looking for, the point X. Okay. This x is guaranteed, and I'll talk about that in a minute, but guaranteed to be the point so that the distance a to x plus the distance x to b is as short as possible. Why is that? Suppose we looked at any other point x prime on line M, drew in the line segment from a to x prime and the line segment from x prime to b prime. The sum of the distances from a to x prime and x prime to b prime are guaranteed to be larger than the line from a to b prime. Why? Because we formed a triangle, one side of which is line AB prime. Two sides of a triangle are guaranteed to be longer when added together than the third side. So AX prime to B prime has to be longer than simply going from A to B prime. What does this have to do with our problem? Well, again, because we've taken a reflection, an isometry that preserves distances, the distance from x to b and the distance from x to b prime are guaranteed to be equal to each other. Also, the distances from x prime to b and from x prime to b prime are guaranteed to be equal. Consequently, the straight line from a to b prime, being the same length as a to x to b, has to be shorter than going from a to x prime over to b. So the answer, the position of the point x here, is the same as the position in the previous problem, asking for equal angles. It's found the same way by calculating the reflection through the line, and in either case, that point x is what we're looking for to solve either problem 3 or problem 4 on that sheet. Of course, if you present these in a classroom, there are some other auxiliary questions as well. Is it, in fact, the quickest path if you're running from A to B touching wall M to touch at point x? It's the shortest path, but is it the quickest? Are there other things to worry about? Is the mathematical model we've drawn here accurate? Might not be quicker to run from A, go in a bit of a curved path when you get to M to get back to B rather than making a strict angle? Probably. And it's a case of the mathematical model using straight lines perhaps not being as accurate as might be needed to solve the problem. Okay. John Wolf is going to answer a question next.
I've got one comment here and 2 questions. The comment I like. This is better than the last conference. Oh, that's a good one to read. The other it's a good one. The other question here, well, it's a comment really too, but I'd like to say something to it. The packages available for secondary school seem to be just demonstration and don't seem to teach the students. Yeah, I think it's very important to, in sort of evaluating software to use in teaching mathematics, to make sure that it sort of exploits the computer's sort of most powerful feature, interaction. We actually couldn't see that in the video sequences that we had here because we could simply shoot the computer images. It's important that the student sort of enters in, his, say on a graphing package, that the student enters his equation and he sees what it looks like, and then he maybe changes a parameter and sees what it looks like. So I do think, I actually agree with this person who called in that a program shouldn't just give demonstrations. It should offer interactivity. And there should be lots of activities where the student can vary the parameters and that sort of thing. And there is certainly a need for computers to take advantage of the there's a need for software to be developed to more fully utilize computers. Okay, the second question here is, what kind of a microcomputer would you recommend for classroom use? I sort of prefer IBM type myself. I prefer the newer computers with higher resolution graphics. So I think that in terms of mathematics instruction, where graphics is so important in graphing equations, that sort of thing, that it's very important to have a computer that can represent graphs very nicely, do geometric constructions very nicely, and that sort of thing. Okay, Wayne Powell now will make a few comments.
First of all, somebody inquired about notice that John Wolfe put up on his computer an example of of descriptive statistics when he used the ogive. And a couple of comments on that, of course, or not the ogive rather, but he used a pie chart is what John used. And the pie chart was where he had the circle drawn up there and then broke it up into several parts to demonstrate what percent of his class were interested or preferred Dr. Pepper or Pepsi or Coke. In his particular class, I guess the percentage favored Dr. Pepper. So I should mention initially that, of course, that was not a very good random sample. It might be something you would try in your class to see if they differ from John's. So John's approach there might work well in the evening news. The second thing about it is people might want to know when a pie chart is appropriately used, because that's completely different from the two forms of representation that I showed. And a pie chart is a kind of graph that's used when you have the total percents of everything working up to 100%. So in the kinds of things I was looking at, we just dealt with frequencies and there was no maximum that something could take on. But when you're talking about a percent of all people, then you can group them so they each take a section of the total pie. So that's where a pie chart comes in. Then there's another kind of graph I'd like to demonstrate for you. If we can get a shot on the overhead camera here, I'm going to show the graph of what's called a pictogram. So I'll put up the name here. And a pictogram is sort of similar to what the word says. It's supposed to be a picture that represents some sort of a situation. So let's suppose in this particular situation that we take some company, we'll just call it Company X so we won't embarrass anybody right now, and suppose that Company X has a stock value of about $100. Let's say that was last week. Okay. Now what happened to Company X is that this week that stock value is now $50. So what we want to do is come up with a good way of representing the change in the stock value of Company X from last week to this week. So the pictogram is the technique we're going to use. Let me turn over the page here and I'll show you how that could be done. One way stock companies sometimes will do this is they'll draw when they send out to their shareholders, they'll draw a picture like this, which is usually rectangular in shape, and there will be all sorts of figures on here. And up here it will say shares of, etc. And this figure is supposed to represent one share of stock. Now what they want to do then is show another box, which is usually, in their case, bigger than this, to show how much the stock has grown in comparison to the size of this original box. But in this case, let's suppose this was Company X last week. And now what we want to show is a similar size box for this week's stock value. Now what it might be tempting to do is to take this length here and cut it down to half, like that, and take the width here and cut it down to half, because we dropped from 100 to 50. So we're cutting this box down in half. So now we put the things here to make this look like shares again, etc. And this would be our representation for this week. But there's a flaw in doing this, and I don't know if the flaw is obvious, but if these things are drawn accurately on my picture here, this second box I've drawn, this and part of the pictogram, is actually only 1/4 the size of the first box. So even though I've cut down the sides to 1/2, I don't accurately represent the loss in stock from 100 to 50, but rather it looks like 100 to 25. So what we have to do is we have to figure out sides. So this would be an incorrect method. What we would prefer to do is to figure out a box that has sides that would be drawn so that the area, again this goes back to the histogram problem, so that the area of this would be half of the area of the other shares. Okay? Now the way to do that, of course, you're going to have to figure out what it takes to multiply your length times your width to come up with an area of 1/2 if this is given an area of 1. But that's not too difficult to do. And that would be the best way to accurately represent the stock change by the pictogram. Well, they tell me that we're about out of time now, so I want to thank you for joining us today. Again, we encourage you to send us a note if you have some questions, and with one final response on that comment that said this was better than the last teleconference, I'd like to tell you that wait till you see the next one. Thank you.